assistant, and he will give us an overview of recent work or the whole long history of artificial language acquisition.
Well, thank you. It is wonderful to be here. Is it too loud? No? Okay. Well, it is certainly a great pleasure for me to welcome you here all in Barcelona. I was immediately enthusiastic when Michael suggested Barcelona as a site, although he didn't tell us that he would bring the weather from Edinburgh to Barcelona. But from tomorrow it will be better. Okay, so well, I also should say that what I'm going to talk about is always the work of a team. And this is a relatively recent picture of our team. You see some people here from Essence, like Jana, who is sitting way in the back there at the last row, and Paul, who is sitting here in the front, you see here. And you see also that we take great care of gender balance in this project. So I'm going to innovate with my talk by starting with a quote from Steve Pinker. And he says, "Language is not a protocol legislated by an authority, but rather a wiki that pools the contributions of millions of writers and speakers who ceaselessly bend the language to their needs and who inexorably age, die, and get replaced by their children who adapt the language in their turn." This is from a book, by the way, The Sense of Style, which I really recommend because it helps you to become a better writer. And so the point here, what is important is the ceaselessly bend the language and also the children who adapt the language in their turn. And this is really the point of view, I think, that we take, which is actually in strong contrast with the view that was held in linguistics in particular, and also in AI, I think, before. Because there was a very strong movement in linguistics which saw language as a kind of garden, you know, a French garden. This is the garden in Versailles, the Palace of Versailles. And you see it's all lined up and nature is carefully trimmed. And so this kind of view is a Cartesian view of language. And of course, the one who promoted this view a lot is Chomsky. And so in this sense, I mean, the people who take this kind of view, they don't believe in evolution. You know, they think language is a static system with fixed parameters, and maybe the parameters change a bit, that new words come in, but basically it doesn't change. Now, fortunately, there are other people, other linguists, who do not accept this point of view. You know, they see language as like, as complicated as the rainforest, right? With trees falling down and stuff growing and evolution taking place all the time. New species, etc., species dying. And so these are what is called construction grammarians or historical linguists. And what they do is they actually go out in this rainforest trying to find grammatical constructions and trying to understand the meaning, and particularly also how meanings change in the course of you know, evolution. And actually, there also, although most psychologists, particularly today, take a very kind of, also a very static view on language, there are some, and I mention here in particular Martin Pickering, who is in Edinburgh, I think, and Simon Garrett, who is also in Scotland. Glasgow is in Scotland, right? They have been studying actual language use and then discovering also that there's alignment going on at every level, you know, the way of semantic representations, the ontologies, the phonetics, the gestures they make, everything is in flux, not just on a population scale, but even in a single dialogue, there is this kind of alignment and interaction. Now, of course, there are also other people, And maybe some of you may have heard about a philosopher called Ludwig Wittgenstein. He had this idea of a language game which will play a big role in what I'm going to talk about. And already in 1955, he was rebelling against the view on language and on knowledge, which was researched by what was called the logical positivists, okay, like starting with Frege and Bertrand Russell and Reichenbach, you know, all of these people. And so they also viewed language as this kind of Garden of Versailles, you know, very streamlined, very strict, not changing. They were universals, and we had to find these universals, and we could formalize everything. And so Wittgenstein emphasized interaction and joint context, and that language was based on communicative intention. And so in this interaction, language is only part of it. He also emphasized that the conceptual basis of language is not fixed and universal, but is negotiated and coordinated and aligned as the communication unfolds. Also that, you know, a lot is not being said, is implicit. So there's a lot of inference going on when we are speaking. And there's also this interlacing of comprehension and production. And there are also the repair actions. That means that if you fail in the language, you know, then we have methods, we have strategies for actually trying to fix it. I mean, this was already clear in the work of Pickering. Well, already the work of Pickering was 40 years after this, but you know, that repair actions, repair strategies were an essential part of dialogue. So this is sort of when we look outside of our own field. And then the question is, what about AI? And it is true that in AI, first of all, is actually, there's a direct line of the work on these logical positivists, the logicians, you know, and AI through John McCarthy, who, as you know, not only designed a great language called Lisp that some of you may know, but also was the one who founded the logic-based approach to AI. And he was a student, actually, of Reichenbach. So this Vienna school, okay, against which Wittgenstein was rebelling, was actually one of the founding pillars of AI in the beginning. And it's still the case that a lot of people in AI just don't accept this idea. Maybe they don't, you know, they don't think about it, but that communication is something that is moving all the time, that is not fixed. So, now there are people who have already another point of view, and one of them is Michael Rovatsos. And he had this vision, this great idea to create this Marie Curie network, you know. And all of you here, well, we are here in Barcelona. We will enjoy the sunshine later today, thanks to him. And of course, we are able to do our work thanks to him. So I really take this moment to thank Michael personally for his enormous effort to create this project. And so he clearly understood the things that I was saying before, you know, and saying, okay, the topic is really the challenge, essence challenge, as he said yesterday, how to resolve communication conflicts in order to make communication robust, resilient, flexible, and adaptive. That's what its essence is all about. So now I'm going to tell a bit of my personal story, how I came into this. And I hesitate between giving you a very technical talk, which I'm happy to do if anyone wants. But instead, I'm going to give you some historical background to all the stuff that has been happening in agent-based models of communication and communication change. And in order to wake you up, because you haven't had coffee yet, right? You're coming right out of your bed. I mean the fellows, I'm talking about the fellows. I'm going to show video clips to wake you up, okay? This is the promise, right? Well, amazing, everybody is listening, you know? I'm competing here against Google and all newspapers and so on. Okay, so how did I get involved in this? Well, in the 80s, well, I should say that I studied linguistics first, and then I studied AI. And I did that in the 70s. I mean, Marvin Minsky was my promoter. And at that time, the knowledge-based approach was very prominent in AI. But then in the 80s, I started hanging out with a number of people like Chris Langton and Rodney Brooks, and we became very good friends. And there are many others, you know, Tom Ray, etc. And with this band of people, we tried to do something revolutionary, you might say. This was the beginning of a field which is called artificial life. Now, some of you may have heard of it. Artificial life basically starts like end of the 80s, you know, first meetings. And the idea of artificial life was to get away from this rigid, strict, mechanical, logic, calculus-style way of doing AI, and to see what the ideas, what mechanisms, what methods we could adopt from biology in order to get to more lifelike forms of intelligence. And this is a book actually from, based on a workshop that I organized with Rodney. The artificial life route to artificial intelligence. That was the idea. Now, some of the other people, they were not interested in artificial intelligence. They were really interested in building chemical, you know, in a chemical way, artificial life, actually real artificial life. Now, this is the kind of stuff that we were doing at the time. This is Rodney, who built a kind of ant-like robot. And maybe I should say that this robot was programmed in Lisp, okay? Of course, with compilers then down to the lowest level of compilation. But Lisp is the key language of AI. If you don't know Lisp, you cannot understand AI, in my opinion. So this is the ant that Brooks built. You know, there were all other kind of insect-like robots here, built from paper clips and stuff you find in Radio Shack. There was also already the work of Mark Raybert, you know, with his hopping robot. And they then formed Boston Dynamics, and they became, I mean, a lot of these people not only became famous, but they also became rich. Somehow, I didn't manage to do that. But Rodney Brooks, he formed this company called iRobot, you know, which built this vacuum cleaner as one of their products. You can buy it here in a supermarket. Now, the things that we built didn't get us any money. Is one of our robots, which is a fish, and which is here swimming in the university swimming pool. And I mean, this is the last time that I was allowed in the swimming pool, actually. And this fish had computers on board and you know, sensors in the two eyes of the fish and a battery. And the sad thing is that wasn't completely waterproof. So we were building this kind of thing, and also we were doing a lot with these kinds of Lego vehicles. This is before Lego actually picked up on this. And part of it was with people in Edinburgh, particularly Tim Smithers. He's no longer there, but maybe you have heard of him. And so what we were building at that time was ecosystems like this one here. Well, here you see this robot in action a bit. And so you see, it's really, this is a poor man's robot, right? We could go and we built our own electronics and our own computing board. The black thing is a camera on the robot. And you see that this robot has an antenna, there's infrared sensors, there's touch sensors. And we built this kind of ecosystem in which these robots had to survive. So basically there were these boxes that were taking away energy from a central energy point. But there was also a charging station in which which you see here, in which the robots could slide, and then with this device, I don't know the name in English, you know, they could get in and recharge themselves. And so we put various robots together in this ecosystem that we built. And the idea was to do various kinds of experiments in cooperation, the emergence of cooperation, the emergence of competition also, but also experiments on how you get fluid behavior in a particular physical environment with sensors and actuators and the whole thing. And so this is the kind of stuff that we were doing, I mean, among many other things. And so this was all fine. But then at some point, I came to the idea, you know, that this is all very good, and there's still many people doing this actually in conferences like Simulation of Adaptive Behavior. You see their work. But was this going to get us to artificial intelligence? Well, I didn't think so. So we had to put new challenges. And then I came to this challenge. This was in '94, roughly. So what would it take to see a population of autonomous robots bootstrap from scratch a communication system to talk about their physical world, including about actions in this world? So this was kind of the research challenge that I put in 95, 94, 95. And this is 30 years ago, right? I think. And so this is still what we're doing. Okay, this is an extraordinarily difficult problem. And of course, the problem of communication and emergence of communication and adaptation, negotiation, sharing, all this kind of stuff has to be solved in order to deal with this problem. So this is, for me, the big challenge, you know, the ultimate challenge of AI that we still haven't solved. And so the first thing, I think, when you do research in AI, the first thing you have to do is to find a challenging environment, a challenging test bed. Okay, this is very different from psychology or linguistics or neuroscience for that matter. And so the challenge that I proposed is to adopt this paradigm from Wittgenstein, the language game paradigm. And basically, what we should do is to set up a population of agents. They could be software agents, they could be real robots. I mean, we've done a lot of simulations in software. They have a set of situations. Okay, so these could be the world that I was showing you, but could be blocks on a table or whatever. And then the game is that the speaker selects a topic. For example, we could be here in this environment and the topic is this. Now, if I want to draw your attention to this topic, I have to conceptualize it. I have to categorize it. I have to describe it somehow. And then verbalize it, you know, give a description of it and transmit it to you. Now, the hearer, or the listener, he has to parse the utterance that he heard, interpret and act upon it. And so this is the game. And so the game is a success if the speaker, if the listener, I'm very sorry about this, if the listener, this is a repair action now, has selected the same topic as the speaker, right? As the speaker. Okay. So, so this is the definition of the problem. And anyone can solve, I mean, or try to solve this problem, right? This is not a solution, this is the problem, this is the challenge. And within this context, of course, we can give each agent basic intelligence like perception, action, scripts for interaction, inference, that kind of thing. And we also can give basic components like pattern recognition, planning, search. But what we should not give to the agents is an ontology or a lexicon or a grammar. They have to emerge from strategies for concept formation, lexicon, and grammar formation. Okay, that's the challenge. And there should be strategies for alignment. I mean, going back to Pickering and Garrett's picture, you know, alignment is very important. So this is the challenge, and anyone can deal with this challenge. And so it's like the prisoner's dilemma, you know, in sociology. Then different people have proposed strategies for dealing with this problem. There's also the issue where these strategies are coming from. So then you could have like an extra layer that the agents do not have strategies yet, but they have to come up with those strategies as well. And so in this first paper 30 years ago, there was not only this challenge, but also a first solution to the challenge. And this was a kind of simple environment, is a grid with agents located on the grid. And then there's a dialogue that they could have, they could point to another agent, they could invent words, they could learn words from each other. And so they go through this kind of dialogue, and there was a proposal for an alignment strategy and all of that. And so the very first results are here. I think this may not mean yet to you, this graph, but to me at the time, this was actually an absolute stunning breakthrough. Because for the first time, we had a population of agents starting from scratch, without a lexicon. And then this is communicative success, reaching in a relatively short time total communicative success. And this is some of the dynamics of the vocabulary formation process, where you see the percentage of agents that agree about or use a particular word for a particular meaning. And so these kinds of diagrams is what we are still making today. And so a lot of people at the time, they declared me completely crazy. And there's still tremendous resistance to these ideas, to my big surprise, I would have thought after 30 years that many people would be already more open, but this is not the case. The ignorance is still incredible. So this was a first demonstration, of course, in a nutshell, right? This is a very simple game, simple situation, not taking into account perception and all of those kinds of things. But our idea was immediately to do this on real robots. So we started with the same Lego vehicles that I showed, and then we were thinking, how could we have communication in these vehicles, And they didn't have vision, or they're very simple sensors on board. And so we had to use the infrared sensors and basically do all sorts of things in the infrared domain that, we cannot see, right? So I'm not going to go, this is in the Artificial Life Conference, maybe the second or the third one, the European Artificial Life Conference. The next one is in York, I believe, in England. Okay, so coming back to this thing here, I'll show you an example of what this looked like. And so basically, these robots, they perceive they turn around, you see, and this way they perceive the environment around them. It's like on this slide at the bottom here, in this corner here, you see. You can't see very well, but this is when they turn around, they see objects and they see other kinds of stuff in the infrared domain. This is their worlds. And where are we here? Okay. And so, then they select a topic, actually, one of the objects in the environment. They do a discrimination game to find discriminating features. They build up this vocabulary and do things like that. So we could port the theoretical model that I showed before in the earlier paper. We could actually port to these robots. Now, most people who came to our lab, they were not impressed. And this was sad. Why were they not impressed? Because you couldn't see anything, right? You see these robots turning around, they have a radio link, they do communication. But it was clear that we had to find another way to make it more clear what was going on. And so then came a second idea, very soon after that, is to say, okay, we need to, we should use vision, we should use spoken output, input and output. And we should restrict the world so that humans can also see the world that the robots are talking about, so that they know, you know, they can follow, right? And so I found these children playing with, I didn't find the children, but I found the geometric figures, and so they could be pasted on a whiteboard, you know, and then we put 2 cameras in front of it. And so the cameras would move around and look at this whiteboard and then see certain regions on the whiteboard and then play a language game about it. And so then they would be starting to talk about left and right and top and bottom and colors and shapes and sizes, you know. And this was something that people could follow. And so we built a setup with 2 of these talking heads, as we call them, looking at these scenes. And we also made a teleportation network. This is all in 1999, by the way, so almost, well, 25 years ago. So the internet was still pretty shaky at that time. And so we had different setups in, there was one in London, one in Cambridge, in Brussels, Paris, Tokyo, and different places. And actually people could get these cameras, plug them in the network, and participate, okay? And this way we could actually, we had the agents loading into a body, you know, using a camera, looking at the world, playing a game, and then they were uploaded again. And so downloaded in another body in another country, perhaps. So this is an example of a setup in Brussels. And, you know, various people played this game. This is actually Ron Langacker, one of the founders of cognitive linguistics, playing with this talking heads experiment. So people could participate. We made a portable version. We made a talking heads website. And people could create agents, launch them on this network, and all this kind of stuff. So I'm not going I'm going to show you a little video clip of it, if I can find it. Sorry that I have to do this, but yesterday night, let's see. Okay, so.
Game 226. Agent Remote, the speaker.
Let me go back. So I'm very sorry. This is from a German television program. This is the only clip I found. And so now and then there's somebody speaking in German over this, but ignore that. So they go to one game,
Game
right?
226. Agent Remote, the speaker, loads into body 2.
Das berühmte Experiment Talking Heads, sprechende Köpfe. Ein Sprecher, ein sogenannter Agent, nimmt über sein Kameraauge eine Figur an der Wandtafel wahr. Er erfindet für das Bild ein Wort. Ein anderer Agent nimmt das Wort auf. Er hat verstanden, dass Wort und Bild zusammengehören.
Game 226.
So this was going on, this was installed actually also in a couple of public spaces and museums, you know, and this worldwide web of agents creating this game, and you could hear the sound of their voices when they were inventing words and doing all this. Anyway, this is the Talking Heads, and I can of course give a whole talk about it, but and this is now a bonus for all of you coming here. There's a new book that just came out at the Language Science Press, and the website is at the bottom there. And for the people of Essence, this book, you can download it for free. Yes, write down the website. Don't load it now, because if everybody is downloading it now, you know, this website will collapse, right? So you press this button, download PDF, and you get it for free. Okay, and I really recommend this book, well, partly because I like the author, but it not only gives you the whole background, you know, it's 400 pages or something like that, but also what happened, and the whole thing was attacked by hackers, and There's all sorts of stories in the book, and I think they are interesting from the viewpoint of the history of AI in the field. Anyway, so I'm halfway of the talk, so I now would like to talk about what happened since those early experiments 15 years ago, okay? And a lot has happened. Now, first of all, there's been a lot of work on theoretical foundations. There's been work on other kinds of games. Then there's been a scale-up in the complexity of the robots. There's been a scale-up in the complexity of grammar and also of the meanings that we are dealing with. So all of these topics are interesting and deserve being talked about. Now, I'm not going to, I plan to talk a lot about this, but I don't have time, actually. But I can tell you that in the domain of the grammar, which became our real concern, well, already in '98, actually, there's a paper in the Artificial Intelligence Journal about origins of syntax in these kinds of agents. But what we have been doing is to design a new formalism, a new grammatical formalism, which is this fluid construction grammar that Emilia mentioned yesterday, and Jana also, which actually we've been working on this for 10 years, you know, with a group of, changing group of people to come up with a new formalism for dealing with a grammar that is in constant flux. And also a grammar that is a construction grammar, which means that it is coupling directly meaning and form together. So this is a whole thing, and construction grammar has been really starting to flourish in the past 5 years, let's say. So I cannot talk about this now. Also in the domain of meaning, we have been pushing up the complexity from simple properties like red, horizontal position, size, you know, those things, going up to more complex, let's say, predicate calculus, at least power, second order predicate calculus, and also doing procedural semantics in order to have the grounding, because we all the time work both with computer simulations, you know, and artificial worlds, if you want, and then also robotic experiments. So I will be very brief on the first two things, but then I think most of you probably would find it the most fun when I talk about the scale-up in the complexity of the robots. Am I right? Yes. Good. So in terms of theoretical work, I mean, if you're interested, well, what happened was that around 2005, let's say, 2004 or 5, statistical physicists discovered this game, the naming game, the language game. And the whole field developed with, I think by now there must be at least 100 papers. You know, we're all studying the dynamics that happens in the games that I showed you before. And so what these people do is they study, for example, the scaling laws. That means if you increase the size of the population, what happens to the moment that the population crystallizes into a shared language? Or what happens if there's a flux in the population? You know, how, or what happens with different strategies? Is there one more efficient than the other one? So now there's this whole field. There could be a complete book just about that. With proofs of the, you know, that some of the alignment mechanisms that we use are guaranteed to lead to the convergence of the conventions in these populations of agents. So there's a whole body of theoretical work, which actually is pretty complicated, and it's only these people in physics, you know, and here Vittorio Loreto is one of the driving people here. Also Andrea Baronchelli is in London at the moment. So these are people from La Sapienza in Rome who play a leading role. But it's not just them, you know, a lot of physicists are interested in this kind of thing, I mean statistical physicists. So I'm not going to go into that. I just wanted to mention also that we have been doing, and other people have been doing, lots of different kinds of games. And so the first started with this naming game, which is really the simplest you can think of, right? It's like giving names. We could play that here in the group, and you know, I call you John, and then etc., and then you call, well, her Emily or something like this. And so how we can get to a convergence of naming just us, you know, just ourselves, right, from scratch. But then there's also naming games, well, like using properties like red and green and blue, and then you have the Gavagai problem, that if you point and you say blah blah or something, is it the color, is it the size? This kind of problems all come up when you do this. There's also a game, a syntax game, which is really about relations, expressing relations. And it's called a syntax game because as soon as you start doing that, you really need grammar in order to dampen combinatorial explosions in semantic interpretation and in parsing. We've done a lot of action games with real robots, which is basically games about an emergent language for asking the other one to do something for you, okay? To stand up or to go to the door. And there are games on spatial temporal games which are about spatial relations, like the box left of the table, you know? And so you get perspective, you get spatial relations, then they get carried to the temporal domain so that you can start talking about time. So this paradigm is big. I mean, you know, I think one of the reviews we got back again, I mean, the reviews we got back is really usually very sad. Not the reviewers from here, but, you know, we send in a paper on a spatial game, for example, and the reviewer would say, well, these language games that was done in the 90s, you know, there's nothing, this is nothing new, right? You cannot make a bigger mistake than say such a stupid thing, right? Because it's a field. It's like saying, well, Galileo did physics, and now you do physics again. I mean, what's your problem? Galileo solved everything. This is a very big conceptual linguistic field, and it's not going to stop tomorrow. Which also means, by the way, that any one of you who wants to become world famous can do things in this field and make really important contributions. There's still many, many open problems. Anyway, so let me talk a little bit for the time that is left on some other robot experiments. And so in 2011, the BBC headline was "Robot Dog Learns Its First Words." You know, and this went back to a paper that we wrote called Aibo's First Words. And by that time, you see, we had all these interactions with Sony, who was building these great robots, and one was the Aibo robot. And I again show you a little video clip because that's what you usually cannot find, but there are papers on all these things. Okay, so this is a naming game, but on the Aibo robots, and also it is, well, we were porting all these ideas also to human-robot interaction, because that's another thing which people fail to see, is that these theoretical investigations with simulations and so on, you know, they say, why do you do all this? Well, I mean, to make communication robust, I mean, I'm going back to Michael's insight, you know, to make it robust, you need adaptivity, flexibility, and all these kinds of things. So this is Frédéric Kaplan, one of the PhD students who made a lot of contributions to this, this whole field. And this is the Aibo here, one of the first version of the Aibo.
Sit down. Good. What is it? What is it? What is it? No.
smiley is another
Bad.
object in the
Bad. Listen. Ball. Ball. Ball? Yes. Good. Good.
Yeah.
Look at that.
Okay, so this is the, I think the BBC was right to see this as a groundbreaking experiment. And, well, again, you know, a lot of people see this experiment and they say, this cannot be right because dogs don't talk. Okay. So then we moved to more humanoid robots. And particularly I could lay my hands on the Curio robot, which you see here. This is a fully, you know, equipped humanoid robot, fantastic robot. Of course, with onboard processors, cameras, 3 cameras actually, sound, production, everything you can dream of, and very reliable. And this here is Michael Spranger, who is one of the PhD students, and this is Martin Lurch. So with the 3 of us, you know, we went to camp in Tokyo where they had all these robots and do all these experiments. And again, there are many experiments we did. I cannot talk about all of them, but we did the same kind of thing in the language game paradigm, you know, creating a world with blocks now. Instead of these fixed things on the wall, there were blocks, and we could introduce new ones and change their positions and do all sorts of things. And then do experiments on, well, multi-word games, on spatial language games, and on things like that. So I'm going to show you one example of this. Okay, so this is a setup, and typically, well, in the beginning, these robots will kind of look around in their world, and then one robot is going to become speaker. This is randomly chosen. So this was the one that was speaking. You could see it because the ears become green. And this one is pointing, you see, to an object that he thinks is Bolima. And then the other robot will give some feedback, you know, like, yes, this was Bolima, right? And so this is one game. Now, you have to realize, again, if you just see that, people think, well, a robot can see because it has a camera, right? But the robots cannot see because they have a camera. You have to implement all the visual processing, all the speech processing, you know, has to work in real time on this robot, right? And it has to get the world model has to be built up. And so this gives you an idea. Well, maybe let me show another game, actually. So this is a game that failed, and then there's a repair action. And so it's through these games, through these repair actions, that these robots develop their own language. Okay, so this is, on the left side, you see what the left robot is seeing. On the right side, you see what the right robot is seeing. And this is on the top, you see the environment, you know, that they are building up. And so if we just do this, okay, so you see the field of vision, you see the different objects that they see. So this was another, this is also this Bolima. It happened actually before the other one that I was showing. And so he's pointing to the blue object. This one is looking whether this is Bolima, and then giving feedback and saying, no, this is not Bolima, right? and then pointing to the right object. So this is a repair action on this particular robot. Now, the great thing about these experiments is that we can track everything that's happening, right? So, so this is a little clip that is showing the insights of one robot, and basically as it is playing this language game over time, and you see the connections between the words, between the prototypes that the robots are building up about their objects, and also between the visual sensations that it has. And the point about this movie shows very nicely the totally dynamic character of the whole thing. So you see these, the blue ones are the words, and the green ones and the red ones are prototypes, and the little squares, they are specific experiences. So that's the picture that is coming out here, is that an ontology is not a fixed thing, you know, that you define once in a file and then it's done. It's something that is all the time changing, new. If you look carefully, you see that these are different sensory channels and typical values for each of these channels. And you see that they continue to change. I mean, none of this is fixed. The concepts, the way they are grounded, the words that these agents are using, you know, everything is in flux. And of course, they get into a stable state as long as the environment is stable. But you see now and then a new word pops up because we throw new agents into this population, or we throw new objects into this population. The whole thing is a complex adaptive system over time. So I think this is incredible, in fact. Okay, so this is the things we've done with this robot, and I'm almost done, so I have to go towards conclusion. But I just want to show one more thing. This is experiments that we have been doing with action language, and the first ones were with the Curio robot, okay, where we did various kinds of things that normally people don't do in research labs. Well, here is one, for example. You know, oh, here is nice. Video can't be played. The file is corrupt. Well, that's sad. Let's take another one. Oh yeah, it's MP4 file. Okay, so a lot we do is that the robots are exploring their own body as part of playing a game, you know. And so we give them mirrors, or we let them stand before the mirror, or look at themselves in the mirror. You know, and they learn about themselves, right? Now, if I would be a psychologist, I would say there's the origin of self-consciousness here, but I'm not going to say that. Anyway, okay, so I'll conclude with one little clip. This is a clip that was made by the BBC, in fact.
Luke is taking me to a lab on the outskirts of the city to show me some robots that are starting to do something remarkable.
Wow. There's 3 of them.
So this is the Muon robot.
And they're much larger than I thought they were going to be.
Built by Manfred Hild. And
these robots have been set up to develop much like a young child does. They're beginning to understand how their bodies work by looking at a reflection of themselves.
You've got a mirror here, so what's the...
Well, the experiment is about that the robot learns something about its own body. Because in order to move in the world, in order to control it, in order to also recognize the movements of another, you need to have some sort of model of your own body.
Right.
And the way that the model is going to be built up is that the robot is doing actions and watching itself performing these actions. So to get a relation between the visual image and movements of the motor. So here you see this looking at its hand, and you also see very much how it's trying to keep balance and
It's pretty impressive, actually.
how all these motor commands are sort of in an early phase, right?
Whoa! Well, cool, sir.
Okay.
It's
real. So it's
just woken up. I know that feeling. It's,
okay.
Yeah.
But it's I think this was a beautiful example of feedback and of finding balance.
It's extraordinary, isn't it? It really does look like it's sort of encountering itself for the first time.
But what's even more remarkable about Luke's robots is that once they're able to recognize themselves, they start to evolve their own language and communicate with each other.
So what's going to happen now?
Well, one of them is going to speak, and then he's going to ask the other one to do an action. He is going to invent a word, because he doesn't have yet a word to name that action.
Right.
Okay, so then he says the word, and this one isn't sure what it could mean, right? This is a brand new word. So then he will make a guess, and if the guess is okay, totally by luck,
Right.
well, they both know this word, and they know for the future they can use this word to communicate with each other.
What if it gets it wrong, then?
Well, if it gets it wrong, then this one will say that this is not what I had in mind,
Right.
and he will show it.
Okay.
I mean,
Yeah.
I don't know which one is going to speak first. Okay, so he's speaking first. He's doing the action.
That's fantastic. No.
Okay, you notice how he looked?
Okay, so now he's recording
getting
what-
the real action.
All right.
Okay. So now there's another interaction going to happen. Again, I don't know which one is going to speak. Okay, now.
Oh, is that the
speaking.
word it just learned?
Yes, yes, yes. So,
okay.
of course, he
it's
knows
almost like checking.
already. So he's
Yeah.
doing.
Yeah.
He's doing it.
And he will say yes, presumably, will he?
Yeah.
So would they even interact with me to sort of learn this language?
Yeah, we could certainly try it.
Right, okay.
Do you remember any one of the words?
We'll see. Yeah,
Okay.
This is quite scary. Oh gosh, it's asked me to do something. Kimatu. It was that, wasn't it? Have I got it right? Oh gosh, okay, right, you tell me what Kimatu is. Oh, okay, yeah, that's right. All right. Tomima. I think that was lifting my right arm. Let's see, did I get it right? Yes. I'm learning robots.
Well, it goes on a bit, but you get the idea, right? And also that, I mean, if you do it between two robots, let's say, you know, you could also do it with people, right, as part of this loop. Okay, so a conclusion. Well, of course, there's enormous technical stuff behind all this, right? There's no miracles here. I mean, there's lots of AI techniques going from vision and pattern recognition, but also to sophisticated grammar, knowledge representation, and I cannot talk about all this. But apart from the book that you, people of Essence, can download for free, there are some other books which, unfortunately, well, most of it is online. You know, all our papers are online, and also software is available. And if you're interested, but I hope that with this talk motivates you to look into these things a bit more. Okay, there's time for 3 questions, 1 minute each.
It works? Okay. So it was very super interesting. Thank you for the speech. And I have one curiosity. I don't know if I misunderstood something, but it's about the strategy of learning language completely from scratch. So I just guessing, thinking about newborn babies, left alone, they cannot learn our language without some knowledge provided by the parents, for instance. So I was wondering if you are testing something with a background knowledge.
Yeah.
Yeah.
Okay. So, so in order to do these things, you need actually two things. You need the learning, you know. So, I mean, without learning, this would not be possible, right? Because if one agent invents a language and the other one cannot learn it, well, it will not propagate, it will die on the spot. So language learning is part of this. But the learning here always takes place in the context of situated embodied interactions. So there's one interaction between two agents, and as part of that, the learner, you know, the listener can learn. Now, so there's no corpus where you go through with some statistical machine learning technique to come up with your ontology or your, it's really built up in a sort of constructivist way, and then, okay. But then there's the other side of the coin, which is the invention, the creative part. And so any time that a speaker cannot express something, for example, does not have a word yet for something, or does not have a construction that can express through grammar certain aspects like argument structure, then the speaker can invent. And invention is not necessarily brand new, you know, a word, it's usually reusing something that already exists. So taking a noun, for example, like Facebook, and then you want to use it as a verb. So you say, he Facebooked me this morning. Okay, so this kind of coercion and analogy and amalgams, you know, this is the kind of strategies that you find in language. And so the two are going together. And actually, if you look at children, you know, they not only passively learn, they actually creatively will invent words and will invent grammar, and they try it out with their parents or with their siblings, you know. And if you have twins, actually, then this kind of inventions will flourish and will become a bit of a secret language between these twins. So I think it's the two parts, and the most of AI so far is looking at the learning, the passive learning, whereas we need the two. We need the creative part and the learning to go hand in hand.
Thanks.
Does the robot recognize if it's looking at its own reflection in a mirror or another robot, and how?
Well, yeah, you raise a very deep question here about the nature of self and consciousness and so on. But, and I have a whole talk about this, you know. But basically, the way that the self arises is in a dynamic way. So it is because there's coherence between the motor control and the visual effect. So if you want, you know, to raise your arm, I mean, and you're looking at an image, and this happens at the same time. So dynamically, there's like one system. Now, if you do this, and you don't see the arm moving, the way you predict that it should have been moving based on your past experience, then this is somebody else. Of course, you get all these phenomena like phantom limbs and you know, people who think their arm is not their own, or they lose an arm and they imagine they have one. And we've done actually, well, it's a bit fun, but experiments where a robot had a stroke, which means a software failure or electrical failure of some sort, but a real one, you know, and then there's one part of the arm which was no longer functioning, and then we tried to do this mirror box experiment of Ramachandran with it, if you're familiar with this. So you know, you can pose all these questions, right, in this context. But usually, if you start working on a particular topic like action language or time or space, you always hit very fundamental problems in knowledge representation, reasoning, learning, knowledge creation, and alignment and all these kinds of things. So that's why I think this is a great paradigm.
Okay, so then I have one. So you mentioned that there's a lot of, you've experienced in your journey through this kind of research, a lot of resistance. And maybe also what I understood is also that maybe some difficulty for people to see how essential this issue of communication is to intelligence and to evolution. Do you have an idea of what the main roadblock is? So if you could go back, what could have helped address that resistance?
Yeah, this is a very good question, and I think we should talk about it. I mean, among us, as part of the Essence project, because I think we all have this problem. I mean, if you believe in these kinds of things. But it is, I don't know, there are many implicit ideas that people have about, for example, about innate ideas. You know, many people think color is innate and color is universal, whereas in fact the facts are that it's not universal. Different languages have different ways to create the color space, you know, and it is also changing over time. And so there's so many points which are part of the common beliefs and common culture, including in AI, but not only there, actually, in psychology or linguistics, so which have to be questioned. So it's a real paradigm shift. And I don't know, there's also like evolution, okay? Many people in linguistics, for example, they don't really know much about evolution. Of course, they know there's a change in species, but to really understand evolution and see its importance, you know, so you have to fight on all these fronts, right? And that makes it so difficult, I think. So I don't have a real solution, because if I did, I would use it. But, and also at the technical level, I notice that there's much more resistance to new ideas today than there was like 20 years ago, 30 years ago. So people, if, for example, in language processing, if you not have a corpus, have a particular test, and then use deep learning, you know, and then say, my experiment here, this parameter gave me 0.03% better than Mr. So-and-so. You know? If your paper is not structured like that, you're not accepted, right? Or we get like a paper back says, this is not about, for computational linguistics conference, this is not about real language, it's about artificial language, so it doesn't fit in this conference. This kind of thing, you know? So, I don't know. One thing I would say is that if you are reviewing papers, try not to be negative. Try to think, how can I improve this paper, you know? And make comments like that. Instead of from your own narrow point of view, maybe there are things that you didn't understand, right? I mean, this is very likely. So I think for the new generation who is reviewing papers, this is one of my main messages. Don't shoot down ideas, particularly when you have new ideas which are very fragile, right? So they have to flourish. So you, instead of just cutting them down, you try to think, what are they trying to do and how can I help these people? I mean, they're not stupid, right? So how can I help them? So I think this is also attitude towards, it's not deep learning, so it's not interesting. Or it's not whatever, genetic algorithm, so I don't do it, or, you know. So, I don't know, we have to, I think it's a very important thing we should discuss in the field. And, yeah.
Okay, thank you very much. Let's thank